Right. Any questions, any thoughts on anything that we covered so far, first of all, from the previous classes? Today is the last one. So I'll be more than happy to take up the questions first, and then we can take it from there. Yeah. Remember the H2O model that we built? That already had a boost, XGBoost, gradient boosting tree, all of that are there. But you can also build them separately, just those algorithms, right? So that, unfortunately, we will not be doing that. But you can definitely do it, I mean, straightforward way in Python. Just a second. Okay. Yeah. Yeah. Right. Right. Yep. Yeah. We'll cover that briefly. Folks, online, can you confirm if you can hear me okay?
Yes, sir, we can hear.
Yeah.
Okay. Okay. Perfect. Yeah. So there are some questions in the class as well. And what we will do, first of all, is to address that, and then we will quickly move through some of the remaining topics, right? Now, compared to what we have listed out, it may not be possible for me to cover all of that, but that definitely will be picked up in the next module, which is the AML, Advanced Machine Learning, right? So the question that we have from Amarnath, let me see, is tagging versus the boosting, right? When exactly we should be using what? So the bagging, the main concept over there is that you have basically the underlying models which have low bias and high variance, right? And in the boosting, you have high bias and low variance. So the bagging, basically underlying models are, if I'm looking at a decision tree, they are going to be complex decision trees, right? They're not going to be simple decision tree. In boosting, you're going to have maybe one or two branches of a decision tree at most, right? So these are more simple learners. These are more complex learners, right? In terms of which one you will choose where, it really depends on your data. So you don't know whether random forest will be the best bet or something else will be coming out. But let's say you try random forest, you try XGBoost, you, huh? Ah, acha, acha. Screen is not being shared. Okay. Right. So all of that, and then depending on what your error metric is or performance metric is for the model, you will choose that, right? Very, very hard to say, even for any model, that given this situation, you should fit this model, right? Very, very difficult for us to say. But random forest will be more simple compared to the XGBoost or gradient boosting tree or something of that nature. So you should try to see if there is not necessarily a big lift coming in going from here to here, then you can choose this. So more simple. So the concept that we follow in any of the modeling is the concept of KISS, right? So keep it simple, or keep it simple silly, as I say it. I mean, as much as possible. If the performance doesn't degrade, keep your model simple. There's no merit in having a more complex model, because that will, be requiring, first of all, more data, high data demand, right? And more important than that, the computation or the compute power will be significantly higher. And you're looking at the time to fit the model also higher, right? So you will try a random forest and then try the XGBoost. XGBoost will take much longer than a random forest for you to fit. So some of those things become a key consideration. If you don't know which model to fit, AutoML will give you that hint that you should begin here and then see how that model performance is with some of the simplistic models, right? Stacking, you will not be able to do manually. I mean, some people do the modeling pipeline, like, I mean, they will say that I'm manually building like model one, model two, model three, but stacking generally is a concept which is more applicable for brute force machine learning, right? So like, I mean, when you're doing the auto ML or you're using a stacked ensemble model, it will automatically stack things, right? Stacking is absolutely pure black box compared to any of the other models, right? You don't know how this input went in and all of that. So stacking works well for cases such as, marketing campaign, right? Or fraud detection, but it won't be the right thing for risk related things, right? Or for which patient is going to survive, not survive, because there you need to have the interpretation of the model. Why are you saying this? What features are coming out more important? Stacking will not have it. It will just say, okay, you should target this person. Even if you go wrong, there's no huge cost associated with that, right? Similarly, fraud, you may have a slightly higher false positive, but not necessarily a big price that you have to pay. But if you're making some decision where you have to justify to any sort of regulatory authority, then stacking will not be a model that you ensemble. Yeah, yeah. You'll have to deploy some other packages, like I mean H2O or like other libraries also. I think sklearn also has a AutoML library. I haven't used it, but I generally use H2O or I use some of the other ones like AutoGluon, which is from Amazon. Some of those libraries, but I haven't tried the stacking model within the sklearn. All right. Any other questions, folks, online before we go on with the new topics for the day today? All right. I take it as a no. So the first concept that we're going to cover today is principal component analysis, right? So let's see if you have gone through it and anyone would like to explain what it is, right? So if I go to my blog, and then scroll down to article number 39, principal component analysis, PCA. And, huh? Yes, that's correct. That's correct. Yeah. Same. Same example. Yeah, the wine data. Yeah, we'll be working on that only. So, who would like to explain what you've understood from the article? Any like guesses also will be fine. Or even if you don't know completely, that's also fine. Anyone? What you understood from this article?
Um, so what I understood is basically to speed up the fitting of ML. Like if it is a 4D or 3D model and it's making the model a bit slow, you can reduce the dimensionality and optimize the algorithm. So and also basically can use for data visualization. What I understood from that.
Okay. The voice wasn't clear, and maybe just want to say it one more time. I hope
Am
my
I
voice
audible,
is
sir?
clear. Yeah,
Yeah.
yeah.
So what I understood from the blog is it's basically to speed up the algorithm. If the model if it has a 3D or 4D dimension and the we feel that the learning is too slow, we can reduce the dimensionality, and that can make the algorithm more optimized and speed up the process. And also, PCA can also be used for data visualization, where
Yeah.
there are some components which we can select, which will have represent the 80% of the variance of the data, and we can use that uh, to change the dimensionality and optimize it.
Okay. Got it. Yeah. Thank you, Anand. Yeah, I think most of what you stated are the right purposes for the PCA. Anyone else?
Sir, so uh, yeah, it is first of all, it is an unsupervised machine learning algorithm, and it is used to remove outliers, various kinds of noise and the errors in the particular model.
Yeah. What else?
And that's it, sir.
Okay. All right. So let me begin with an like a simple example. Let's say you have dropped a coin, right? And if I tell you that the coin is there on this floor only, on one dimension, right? So from here to here, it'll be easier for you to find that coin, right? Where exactly that is dropped and you can detect, right? So then I can say now the coin is not in this floor, but in this room. So now you're looking at that three dimension. So it will be much harder problem for you to find that coin, right? Now, if I tell you that the coin is not just in this room, but it could be anywhere in this building, then it's going to be even more difficult problem for us to solve for, right? Same thing happens with the dimension. So if we are trying to look for a signal, like what are the features which explain the dependent variable, and if I have n number of features, it becomes an easier problem for the algorithms to pick up because they have to only look at that many features. But if the number of features keep on exploding compared to the number of samples that you have actually given, then they cannot really detect the signal or separate the signal from the noise. And that is what we call as a curse of dimensionality. As the number of dimensions go higher, the amount of data that it will be required to learn the model will go exponentially higher. And that amount of data generally is not possible, right? So that's why you have to reduce the dimension. So that's one thing which is basically in terms of the dimension where it plays an important role that you are looking at the number of features which the algorithms can manage, right? That's one thing. The second thing is we spoke about the assumptions in the linear regression. One of the assumption in the linear regression was that the features do not have the correlation or there is no multicollinearity, right? And if there are multicollinearity, your model's coefficients will be wrong. There are other models also which actually don't behave very well when you're looking at the multicollinearity. So it helps you addresses that, right? So reduce the dimension, fix the multicollinearity, make the signal separate out from the noise, right? The third one is when you're looking at a data which is, let's say, thousands of observations, right? And hundreds of columns and features. If you don't do the principal component or something on the similar like an LDA, for example, right? Um, the amount of training that will go in the model will be very high. So the compute basically in terms of training the model and letting the model learn the behavior will be very, very difficult problem for us to solve. So it basically helps in three or four main ways. One is basically separating the signal from the noise. Second is in terms of making sure that the algorithm's assumptions are not violated. Third is the fitting time itself will be reduced. And the fourth one is going to be that you have like the time. I mean, we have already spoken about the time, but I was talking about something else, right? Yeah, anyways, I think those are some of the main ones, right? So in terms of making sure that you are not necessarily overloading on the features, right? So that's the main thing. And there is, a logic behind how it happens. But I will just talk about some of the main ones, right? So it basically uses covariance metrics, right? So let's say if you have n features, so it will be doing n by n covariance matrix. Covariance is how one feature varies with respect to another feature. So if I do a covariance of variable x1 to variable x1, the covariance will be 1 because they are linearly correlated, right? If I do, something which is 100% negatively correlated, let's say variable x4 to x1, then covariance will be -1, right? So basically it does that which variables are related to the other variables, and then it does a matrix transformation In order to do that, it basically forms what we call as a components, right? And I'm just going to talk about what those components are. I'll begin with a baby example. Let's say I have 5 variables: x1, x2, x3, x4, x5. After I do the PCA, and there are certain steps involved in doing the PCA, after I do the PCA, it will form 5 components: P1, P2, P3, um, P4, and P5. So the number of components by default will be equal to the number of features, right? But what are these components? These components are nothing but the linear combination of your x variables, right? So for example, alpha 1 x1, alpha 2 x2, alpha 3 x3, alpha 4 x4, and alpha 5 x5. What will be the P2, for example? It may be beta 1 x1, beta 2 x2, and so on. What could be the P3? Gamma x1, gamma x2, and so on and so forth, right? So that's the crux of the PCA, right? So they basically form the linear combination of the original variables. But there's another beauty to it. They form that in a way that the correlation between P1 and P2 will be 0. That whatever P1 captures, P2 does not capture the same thing, or they are not necessarily linearly correlated things. What we call in the statistical languages that they are orthogonal components. So P1 and P2 are the orthogonal, right? So that's what basically the whole singular value decomposition, the covariance matrix, and there are concepts related to that which I will talk about, which are eigenvalues and eigen vectors, right? But that's what basically they do without going into much mathematics. Now, you may ask, like, if I have 5 features and I get 5 components, then how come I'm doing a dimension reduction? So does anyone know the answer for it? How was the traffic for you folks? Crazy? Very bad, right? Yeah, a lot of flooding in different places and all of that. So what is the main utility then if I form the same number of components as a number of features? Anyone knows the answer if you have read the article? Why is it called dimension reduction then if the number of components are exactly equal to the number of features? Okay, I will tell you. So generally what we follow as the selection criteria is that we choose the number of components which explain 80% to 90% of your original data's variance, right? And I will talk about that when we do the modeling. So we don't necessarily choose all the components, right? So maybe if I choose P1, P2, and P3, they themselves will provide me 90% of my original data's variance, and I will define you how that variance is actually computed. So basically what happened, let's assume that this is the fact, right? That I mean, I choose only 3 components, P1, P2, P3, and they give me 90% of my original data's variance. So the number of features we started with were 5. The number of components we went down to is 3. So how much is the reduction in percent? Can anyone tell me? So that will be 2 divided by 5. Around 40% drop in the number of dimensions with only 10% drop in the explainability, right? So that's the main thing. So you're making a trade-off that you're saying, okay, I'm willing to let go of 10% of my original data's explaining power, but I have dropped my number of variables by 40%. So it's a fair trade-off. Like, I mean, everything has a cost associated with that, right? So the cost you're willing to pay is that I can let go of 10% of the explaining power as long as I'm getting a significant drop in the number of components. So that's what basically they do, right? And I will just give you a walkthrough of my code first. The article first, and then we'll talk about that. So we spoke about the curse of dimensionality. It helps in detecting outliers, removing noise, speech recognition, many different areas, right? How do we choose the right number of components? Like I said, I mean, you should choose a number of components which actually explain 80% of your original data's explaining or the variance that we had there. Or they should have an eigenvalue of 1 or more. What is an eigenvalue? Eigenvalue is related to the concept of the matrix, covariance matrix that we've computed. And for plain English, you can assume that eigenvalue denotes how many variables worth of explaining power each component has. So let's say, going back to our example, if this component has eigenvalue of 2, this component has eigenvalue of 1.5, this component has an eigenvalue of 1. That means principal component 1 has the information that were captured by two variables originally, right? So that is the explaining power that principal component 1 captures. Similarly, principal component 2 captures 1.5 variables worth of explaining power, and principal component 3 captures 1. And whenever you form the components, you will see that the P1 will have the most explaining power. P2 will have the second most explaining power. P3 will have the third most explaining power, and so on and so forth, right? So it will be never haphazard that P2 is more explaining than P1. So it will be always P1 is the most important, P2 is the second most important, P3 is the third most important, and so on and so forth, right? So that's how basically we go through. So that's the second rule that we have. And the third rule is similar to what we're going to talk about in the clustering, which is the elbow method, to see where exactly this makes sense, right? So what I'm going to do now is shift gears and give you a walkthrough of my code first and explain you what we're doing, and then I'll walk you through line by line. And then you can actually start typing in. And one of the things that you have to really ensure that you do before the PCA is scaling. Does everyone remember what is a scaling or normalization of the variable? Yeah, anyone needs a refresher? All good? Correct. So make all the variables comparable. So without scaling, your PCA will not be effective. So you have to definitely do the scaling to really make sure everything is on the same scale before you move on. That's a must-have for you to do, right? And we will go through that flow. So let me just run few lines of code because I'm doing the random forest over here as well. So that will sort of like, take some time, but I'm gonna just walk you through the PCA flow first. Yeah. Just a second, I'll come there. I just want to make sure that I'm looking at the right code here. Yeah, it is the right one. Yeah, go ahead. Hmm. Hmm. We never do the scaling of the y variable. Y variable will remain what it is. Yeah. Yeah. All the features. No, it's not necessary because what you're saying, trying to say, scaling is like this. Like, I mean, let's say you have to identify an outlier or I mean, an exceptional performance, right? So think about a kid who is studying in the 5th grade and you're comparing that kid to a 9th grade kid, right? So you cannot give them the 9th grade syllabus and say, show me that you can solve these problems, right? You have to compare with the 5th grade syllabus and say who are the top performers. Similarly, the 9th grade kid, right? So that's where the normalization is happening, that with respect to you, the max I can expect is this that you should be knowing. And the kid demonstrates that. So you can say you're the top performer. Similarly, for the 9th grader, I mean, you cannot ask them a 5th grade problem and say you are a top performer, right? So that's what we're saying. And we're saying this variable x1 ranges between 1 to 1 million. So 1 million will be 1 for me and 1 will be 0 for me. Now, any number which is there between 1 and 1 million will be between 0 and 1. Similarly, for another variable, which is, let's say, between 1 and 10, I'll say 10 is 1 for me and 1 is 1 for me. And now everything else in between will be rationalized based on that. So that's the concept of the scaling, right? So I will just give you a walkthrough first. People don't try to type anything. I'm just going to walk you through some of the code here first, and I'll zoom in and then give you the chance to start typing. So the first thing that we're going to do, I'm going to run line by line, is the multiple print command that we have, right? So it's going to connect and run. So that's the first thing. The second thing we are doing is we are importing the wine data that we worked with last time. We will do some exploratory analysis, right? We will do the features and label separation. Then we will do the scaling over here. Then I'll walk you through each line of code. I'm just running the portion that I'm interested in. And after doing that, we will import the PCA object. We will fit on the scale data. We will display some of the characteristics of the PCA, which I'll explain you later on. Then based on this, we will select n number of features, and we will see how much variation we are able to explain. Then we will convert our original data into the PCAs, right? And then we will plot those PCAs. We will show you what exactly happened after the PCA, right? Then we are displaying the principal components, and that's the flow, right? So let me just go step by step. For each of the step, let's make sure that you've typed the code and you are good to go. So the same Wine code that I shared with you last time is the same thing. So please confirm once you're done with line number 1 and 2, which is just importing your data, running the magic command as we did last time. I shared the code also, Wine code with you. So that's the code that we're looking at. Let me know once you're good to go. Folks online, I hope you are clear. We are typing line number 1 and line number 2, and I'm waiting for your confirmation once you're good to go. And this is something I already shared last time. Done? Hmm? Yeah, yeah. Which one?
Done.
Okay. You talking about the previous class? Okay. So let's just focus this one, huh? Yeah, go ahead. Question online. Oh, okay. So you're saying done? I think somebody spoke that they're done. Okay. All right. So I'm gonna take it as a yes from everyone. Anyone who's struggling, let me know. Otherwise, we'll move on.
We can move on, sir.
Okay. So then third thing that you're gonna do is just some exploratory analysis. Totally up to you whether you want to do it or not, right? But you can just take a look at what we are doing over here. Find out anything interesting. Just convince yourself that you understand this data. Whatever you want to do. I have done some of the things over here, but it's up to you what you want to do. So you can do info, head, sample, tail, histogram, whatever gives you the warm and fuzzy feeling about the data, right? And I'm leaving it to you because that will be one of the things that I'm gonna ask you in the exam as well. When you actually have a brand new data, what exploratory analysis you did, what you understood, why you chose a certain thing, and all of that, right? So that will be something that will be totally dependent on you. Shall we move on? Okay, so assuming everybody is good to go, we will do the features and label separation. Remember, the scaling does not happen on the Y variable. So before you do any sort of scaling or normalization, you have to separate out your X variables from your Y variables, right? So that's what we are doing. So let's create those two features, two arrays, one with the features, the other one with the label separately. Something similar to what we've done a number of times in the modeling so far. All done? Okay. So once you create the features and labels separately, as we have done in the previous classes, this is where the scaling is happening, right? So from sklearn pre-processing import scale. Now this scaling is, can anyone tell me what is the difference between this scaling and the min-max scaling? What is it that this scaling will do or the min-max will do? And do the step first and then tell me what do you think this scaling is doing to the data. Let's see who can interpret once you generate the output as well. The output itself will give you the hint that I have done this. This will take what? Yeah, you can look up also, Google also you can do. The idea is to find out what is the difference. Min-max scaling can be done between any value A to value B, like 0, 1, minus 1, 1, 0, 10, whatever you want to do, you can do that, right? This is doing something different. And there's no reason why I've chosen that versus the min-max. I mean, you could choose either one of them, but I just want to demonstrate that what does this do. Yeah, any ideas, Amarnath, what this scaling is doing? You done? Look at the output, describe. Look at the describe output. What is the minimum? What is the maximum? What is the standard deviation? I'm giving you some hint. No, this is not the right output. This is only the head, right? But like the describe will give you the right information. Look at the describe output. I'm not scrolling down because people are typing. Hmm. Mm-hmm. Correct. It's not between 0 and 1. So it's not the min-max scaling. Yeah. Mean and standard deviation. Yeah, that's correct. Yeah. What about it? Subtract the value from the mean and do the average. Okay, so what is it called? I mean, divide by standard deviation. Does it ring a bell? No? I think that's good enough hint. You are subtracting the values, or I mean, you're subtracting the mean from the values actually, and then dividing by the standard deviation. Okay, so I think maybe you folks are not aware of. So you're aware of this in the statistics class, you would have gone through it, right? So let's say I'm looking at this sort of shape. You're aware of this? What is it? It's called the normal distribution, right? So this is called the normal distribution. What are the characteristics of the normal distribution? That there's going to be a certain mean, and then let's say this is 1 sigma, right? So this is negative side. So this is negative sigma. This is positive sigma, 1 sigma basically. 68% of the observations will be lying over here, right? This is, you can imagine another negative sigma over here, another positive sigma over here. How much observations? Anyone? Correct. 95% observations will be lying over here, right? And then finally we have, yeah, another negative sigma over here and another positive sigma over here. This is basically nothing but plus minus 3 sigma. And you'll have 99% of the observations lying over here, right? So this is what the normal distribution is. Now, what we are doing in this scaling is what we call as a standard normal distribution, right? What is a standard normal distribution? That you will make the mean 0, standard deviation as 1. So a specific normal distribution which shows mean as 0 and standard deviation is 1 is called a standard normal distribution. So basically, when you are doing this scaling, what is happening is you're doing a z-score, right? So you take x minus mu divided by sigma, right? So that's what you're talking about. Sorry, I forgot your name. Huh? Aditya. So that's what Aditya was telling me, that we are subtracting the mean from the actual values and divided by the standard deviation, right? So that's exactly right, Aditya. So we are computing the z-score, but not all variables will follow a standard normal distribution. So you're going to have certain outliers, right? So there's nothing that will tell me that the shape will always be like this, right? So the shape could be like this also, right? So it could be like this, right? Like it's not a normal distribution. So that's why you're going to see certain values which will be more than 3 also. So for example, 3.78 or 4.78, right? These are outliers basically, right? So even though you're doing the scaling, they continue to be there, but they're not there in a massive scale. They are like, in a reasonable scale. So 3, 4, 5 and all of that. So now it becomes much more apple to apple comparison between the variable. And that's the motive of doing this standard normal distribution. You could have done the min-max scaling also, doesn't matter. So now you can see, going back to what Avanath you were trying to explain. So for each of these variables, mean is 0. You may not believe that this is 0, but this is 0. Actually, e to the power minus 16 is 0, right? So let's see if we can round off this to make it much more pretty, right? So let's do np dot round. And let's do 2 decimal places, yeah. Okay, I have already done this. So what I'm going to do is basically next line, because it's gonna otherwise not like it, right? So, okay, now you can see the mean is 0 and standard deviation is 1, right? For each of these variables. So that's what basically the standard normal distribution does, that it will take your variable, subtract the mean from it, divide by the standard deviation. So you normalize for the standard deviation of the data, and you will make a standard normal distribution. So each variable is now converted into a standard normal variable. And that's what we're looking at. Just a second, yeah. Hello? Yeah. A402. A block 402. somebody at home. So that's what the standard normal distribution does. Any questions, folks? Anything which is not clear? Now, the max will not be 1 because I said max will be somewhere around 3, right? So depending on the outliers, whether it's a positive skew, negative skew, right tail, left tail, all of that you're aware of. So for example, this variable I can tell has more outliers. Why it has more outliers? Because the values are significantly bigger than 3. Because if it was a standard normal distribution, 99% of the values should be between -3 to +3. Yeah. So 75% is over here. So you can see there is a big distribution in this variable, which is okay. I don't worry about fixing the outlier as of now. I just want to make sure that they are on a comparable scale. So this is now much more comparable. Max values are like apple to apple comparison. So like, I mean, it's not necessarily very different, right? Versus the max values over here, I think we would have done that somewhere earlier on. Or if not, then I will do it now. So if I do wine dot describe, right? So you could see the values were looking very, very different. So for example, for this guy, the value was only 3 as a max. For this one, it was 162. So this variable will never have a chance against this variable because it's just like apple and oranges, right? I mean, very, very different scale altogether. But after doing this fixing, which is sorry, I mean the class level of course will have a lower range. But let's say malic acid, the max there was 5.8, and alkalinity variable had max, sorry, or magnesium had the high of 162. Now let's go and take a look at this. So again, remember malic and magnesium both starting with M. After doing the scaling, malic is 3.1 and magnesium is 4.3. Not that bad, right? I mean, from 30 to 160, which is 5-fold bigger variable, now I actually made them much more in line with each other. And that's the whole purpose of the scaling. Any questions, folks, before we move on? All good, Dinesh? Yeah. Which one? Because it's all distance, like the coefficients you're estimating. So when you're estimating the alpha, beta, gamma, like remember the line that I was showing you, like these coefficients, they will not be very accurate because it's a linear combination. And even in your linear regression, for example, when you want to make an apple to apple comparison, which variable is more important, you have to normalize it. Because then you can say the coefficient for this variable is bigger, coefficient for this variable is smaller, and hence this variable is more important. Because if you have a variable in a much bigger range, the coefficient for that variable will be smaller because only small change will transform into a big change in your dependent variable, right? So that's why you have to normalize things. Okay, I
Sir,
take it
one,
as that
one small
everybody.
question. One
Yeah,
small
please,
question.
please.
So, what is the advantage
yeah.
of doing this way? Not, I mean, than a normal, I mean, min max. Do we get any advantage over this?
Yeah, can you tell me what do you think? I mean, what is the min and max value in the min max versus min and max value over here? What do you think is the difference? What will be lost if we do the 0, 1 versus the standard scalar? What information we're going to lose?
Maybe the I mean number variability itself, because I mean if I see alcohol level it is around 178 and something like that, whereas if I do that in a min max, like okay, between the 0 and 1, so there are certain characteristics which may lose out.
Yeah, yeah. The correct answer there is, building on what you're explaining, is that the amount of the outliers that you have in the data will be lost if you do the 0, 1 versus a standard scalar, because standard scalar retains that. Like it will tell you that variable x1 has this sort of tail, variable x2 has this sort of tail, right? When you do the min-max scaling, everything is capped between 0 and 1. Now you will see that the extreme outlier will be 1, but what is that outlier magnitude vis-a-vis the other thing? So that shape of the data is lost if you do the 0, 1 scaling versus doing this, right? So min-max scaling is a way to go when you have a large number of data where you don't necessarily need to look at the distribution of the variables and so on and so forth. Standard scalar works better when you still want to keep an eye on how variable x1 compares to variable x2 and so on and so forth in terms of the amount of the outliers that we have, right? So it retains that shape for you. Correct. Correct. Yeah, absolutely. Because see, any algorithms that we have or any methods that we have, we don't know what is going to work specifically for that data that we're actually looking at, right? So what people do is they will not even do like different models. They will try the different scaling methods as well. So imagine like, I mean, I'm going to do a min-max scaling, then I'm going to build a model, see what comes out. I will do a standard scaler. I will again try it out. I will do a min-max scaling with 0, 1 and then 0, 5 and then see what comes out, right? So it just really depends on what model comes out best, right? And like, you know, in olden days, I mean, when I say olden days, not necessarily like, I mean, 19th century, stuff like that, I'm saying 10, 15 years back, models were built mostly as a craft, right? So you'll have a professor in maths and statistics and they'll say, optimize using this way, that way, right? Those days are gone now. You need to understand the concept, but you need to try multiple things because the data itself is becoming so complex. Like whatever you knew yesterday about that data, the pattern has changed. So the same thing that worked yesterday will not work today. So you have to keep on trying what scaling methods, what preprocessing, whether I should replace with the mean or median or a specific value. You have to try it out multiple times and then it will come out, right? So that's where the model development is not about your intuitive sense and so on and so forth. It's more about trying different techniques. What is more intuitive now in the entire modeling process? Can anyone tell me where exactly your brains will go? Where exactly your biggest thinking will go in the entire modeling process? The biggest amount of time where you should spend now, given that you have so many different techniques. Feature engineering. So just understanding what your features are. Shall I create another feature by numerator denominator? Shall I create an exponential of this variable? Do something different on that variable? Do I do the mean value treatment or median value treatment? Do I replace with the mode or replace with the missing? That is where your human intelligence will come in. Building the model is the very little human intelligence. Very, very little. You cannot beat a machine, period. The machine will only look into the data that you feed it. So that's where your intelligence will go in, how good the data that I can feed in, right? Machine doesn't know domain knowledge. It cannot tell that this is an automobile versus an airplane. You know the difference, right? And that's where you have to tell them, like, you know, what exactly are the things that you're looking at. So the feature engineering or the data cleaning, data pre-processing, the dirty stuff is where you will be required, not the more glorified building the model. That machine can do it, right? So that's where, I mean, the real skill comes in. So when you see that, I mean, I am competing in Kaggle, exactly the same data, right? And let's say I'm looking at the ROC as the metric, right? A receiver operating characteristic curve. Somebody got 0.76, the other person got 0.79. More likely than not, they all tried the same techniques, but the person who came on the top was able to do a better feature engineering, which is a dirty job. Like, I mean, for example, the text data that you have to do the regular expressions, replace that with a certain value, do a lot of those things, which takes, you know, hours and hours, if not days and weeks to really fix the data. And nobody likes to do it. If you say, okay, what would you like to do, Aditya, for example, build a model or do the data cleaning? I'll say build a model, right? But who's going to do the data cleaning then? So that's where the challenge is. Okay, let's continue. All right, so we just did this. I'm not going to build the model right now. I will jump directly to the random forest now. So if you want to do, in what? In building model? Yeah, readily available, but not readily explainable. So that's where your role really comes in. So even if you're using an auto ML model, right? Somebody has to do the explaining. Somebody has to type what exactly you built, why you've chosen those parameters, why it makes sense, what are the features that you're looking at, How do we really maintain the model's health over a period of time? That's where the data scientist or the research scientist will come in, right? The techniques keep on evolving. Given the data that you're looking at, I mean, what should be the right model that you're going to try, right? So it's not that like plug and play. So even though there are a lot of auto MLs, very little work in the industry really happens on the auto ML. Last time I spoke about, they are more like a benchmarking sort of thing. Like, I mean, you can see what sort of more performance I can expect, right? Because they become completely a black box model, right? And that's where you will come in and say, no, I can simplify that, right? And I can make it much more interpretable and all of that. Huge focus on model interpretation. Huge focus, right? Because nobody likes to be told that this works, but I don't know how it works. Models keep on evolving, yeah. It's mostly the research people do. Like I mean, if you look at the different level of hierarchy, there are people who are research scientists, right? I mean, versus people who are data scientists. Data scientists will try what exists as of now, but do the best possible model. Research scientists will say, let me try to do something on top of that. Let me figure out what really works on this data. They will come out with a brand new technique. So let's say I will call RP boost as my model. If I tried different things, right? I mean, so I can come out with my own model that, I mean, I'm doing this way gradient optimization, that way scaling of the variables, and this much pre-processing in that package, right? So that could be a brand new model. And then that's correct. That's correct. And it's always 80-20. For 80% of your job, these 20% of the models that we're talking about will do the job. You don't need to build anything more sophisticated, right? Only for very, very hard problems that we're trying to solve for will be advanced models required and longer training required and more data required. All of that complexity will come in, but it's always 80-20. So whatever you're learning right now, that will work for 80% of your business problem that you're trying to solve. All right, so this is where the scaling really begins, right? So I will zoom in a little bit more and please make sure that you type the code. So what are we doing? From sklearn.decomposition, import PCA. PCA is a short for principal component analysis. Or some people in statistics call that factorization. And then what we're going to do is we are creating this instant and I'm mixing two steps together. So instead of creating PCA and then doing the PCA fit, I'm doing together. So I'm creating this object called PCA, which is taking this instant PCA and I'm doing the fit method and I'm fitting it on the scaled variable, X array scaled. Remember, we never fit PCA or do any scaling or anything of that nature on the Y. Only X or the feature space is treated, not the Y variable. Y we leave alone as sacrosanct. Yeah. Everyone done online? And when you do a PCA, it will just show a PCA, nothing else, right? I mean, but we're going to talk about what exactly it does and all of that. That's where the real meaning will come in from the PCA. Now, how many original variables we have in this data? Who can tell? The original data X, how many X's we have? 13. Okay. Aditya says 13. So how many components will be generated by default?
13.
The number of components will be exactly equal to the number of features that we have, right? So it will be generating 13 components, right? So let's see. So after doing the PCA, I'm talking about this particular method called explained underscore variance underscore ratio, right? And you'll see that this array will have 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. These are the components, right? So I'll just explain what these numbers really mean. But go ahead and run this line also, line number 7, which is np.round, numpy round. PCA is the instance that we have created and fitted the data on it. Explained variance ratio and round it out to 3 decimal places. Hello. All right. So what these numbers are? Can anyone explain? Or I mean, any intuition? I think look at the line number 7 and 8 together, and then let's see what you can tell me. So first of all, we agreed that these are nothing but the components, and then we're looking at explained variance ratio. So what do you think this might mean? Shivalsa, any idea?
These are already
Okay, I will tell you. Sorry, go ahead.
I
Go ahead.
see these are already in descending order.
Hmm.
So
Yeah.
so this means that it has got how many? All 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 14 components, and which all
13
components,
13 components.
13,
It
and
should
which
be
all
the same as the number of features, 13 components.
yeah.
1, 2, 3, 4, 5. And you can, of course, do
Is
the
it a
shape and you
eigen?
can quickly.
Is it an
Hmm?
eigenvalue, sir?
It is similar to the eigenvalue, but the interpretation is more simple, right? So I'll just tell you. So this says that your component number 1 have 36.2% of your original data's explaining power. 36.2% of your original data's explaining power is being captured by principal component 1. 19.2% of your original data's explaining power is being captured by your second variable, right? Remember, they will always be in the descending order. Third component has 11% of your original data and so on and so forth. So if you add them all, then that's your 100% of the data's explaining power, right? So that's what basically we are looking at. So it basically confirms that principal component 1 is the most important component that we're looking at. Principal component 2 is the second most, and third is the third most, and so on and so forth. And you can see by the time I come to this last component, it is only explaining 0.8% of the original data's explaining power. So almost nothing, right? So that's why we will chop them off to say how we should choose the number of components. So that's the one thing that we're looking at. So I'll just explain you. So then what really happens is, I mean, how many of these components I should add up to get to 80% of the data explaining power? Can somebody do the math and tell me? So if you add up 0.36, 0.19, 0.11, 0.071, 0.06, so on and so forth, where do we get to 80%? Correct. If you sum up the first 5 or 6, tell me where do we get the 80% of the original data explaining power? How many components are required for it? First 5 components, right? So if you add them up, 36, yeah. So first 5 components will give you the 80% of the data's explaining power, right? So that's why I'm in the next step. Instead of doing a regular PCA, what we're gonna say is build a PCA with 5 components, right? And let me see if I can pop up the help also. So you can see this is how basically it's gonna work out. N components is how many components you really would like to see in your data, right? So when I fitted that originally, I left it blank. So I said none. That means choose as many features as you would like to, right? And the rest of the things we left it alone. And SVD solver is auto to really figure out the right linear combination, so on and so forth. Now, because I know 5 components will give me the 80% of the data's explaining power, I'm gonna choose 5. Let's say your business is not 80%. I need to have 90%, right? So I can always go and say, let's say, what is happening? Okay, nums lock is not working. So let's say 7. I can fit a PCA with 7 components. I'm getting close to 90%, right? So let's say for whatever reasons, your stakeholders say I must have the PCAs which are explaining 90% of the data. Then in that case, I would have to choose 7 components. However, let's just go with the 5 components as of now. And I'm explaining 80%. So original number of components or original number of features were 13, right? So we did a dimension reduction where we came down from, 13 x's to 5 components, which is a reduction of what percent? Can tell me what is this x6%? So that will be 8 divided by 13 is the reduction that we've done in the number of variables, right? So what is that number? And then original data's explaining power was 100%. Now we are down to 80%. So that's a drop of 20%. What is this number? Anyone? 61? 62? Okay. So you can see I have reduced the that I'm paying for that is 20% drop in the explaining power. And that's the utility of the components, right? That I have almost more than half, I have reduced the number of variables, but yet I still have my original data's explaining power captured over here, 80% of that, right? So I have basically removed what we call as a noise, and I'm focusing on the signal, right? That because I don't want to have like every single nuance in the data. I want to focus on the main things which are there in the data, right? And how do we define the main things? 80-20 principle, that I want to capture the 80% of what we originally had. And then you can see the trade-off I have to make. 20% drop in the information, but I reduce the number of components by a staggering 62%, right? So that's the crux of the PCA. But we'll go on and show you some other things as well. This is what the eigenvalues are, right? So after we've done the PCA with 5 components, I'm saying explained variance, not explained variance ratio, but explained variance, right? Which is 4.7, 2.5, 1.45, 0.92, and so on and so forth. The way you interpret this is these eigenvalues, or some people call it eigenvalues as well. I don't know what is the right pronunciation. I call them eigen, right? Because it sounds better. So eigenvalues over here, 4.7, that means the original principal component 1 have 4.7 original features worth of explaining power. So one component packs the information of 4.7 features. Second component caps the explaining power of 2.5 variables, right? So you can add up. So very quickly, you can, for example, do the sum of this also. And you can see I'm roughly saying that I have lost 2.5 features worth of explaining power, but I'm still having 10.5 features worth of explaining power with me, right? So that's the concept of the explained variance ratio. I'll just remove this and then go back to this one. So another rule of thumb that people use is any, that may be slightly like, because we don't have a particular random seed, right? So that might be slightly different, but it shouldn't be like day and night different. What is the value you're getting? Not the ratios, yeah. These are the eigenvalues. These are the eigenvalues, right? Okay. Is everyone with me in terms of the concept and the code till line number 26? Yeah, all good. These are the eigenvalues, which is the way you interpret is the principal component 1 has 4.73 variables worth of explaining power. Remember your Malik said all these variables that you had originally. So it says, okay, I have combined all of them linearly in a way that I can tell you this principal component 1 alone can tell you 4.7 variable worth of information. That's how we are doing the dimension reduction, right? Because it's creating those linear combination and capturing the information in a way that I can tell you exactly the same thing, right? I will do one more thing, folks. I mean, and I'll, you can do that in the right sequence. But now what is happening, anyone can tell me? PCA underscore PCA dot components basically will show you the component details, right? I told you that, I mean, it's going to be a linear combination. And then I'm adding the column information over here, right? So this is what your PCAs look like. So remember, I have formed 5 PCAs now, 5 components, 1, 2, 3, 4, 5, and they're all linear combinations. So if I just take a moment and sorry to jump back and forth, I explained you that PCAs are nothing but the alpha 1 x1, alpha 2 x2, alpha 3 x3 linear combination of your original variables. And PCA estimates what is this alpha 1, alpha 2, beta 1, beta 2, gamma 1, gamma 2 values. These are nothing but these which have been spitted out. So basically, principal component 1 is nothing but 0.44 times alcohol minus 0.24 times malic acid minus 0.002 times ash and so on and so forth, right? So that's the linear combination that we spoke about. Completely not necessary, but this is just for your understanding, so you know what those components are. When you're fitting the PC, it's not a necessary step. All good? Shall I move on? So then what we're going to do
Sir,
is...
just a minute, sir. Just a minute, sir.
Oh, okay, okay. No problem. No problem. Yes. So alpha 1, bit alpha 2, these are the coefficients, right? So for example, if I just look at this line, PCA1 is nothing but 0.44 times alcohol minus this time malic acid, this times ash, this times alkalinity, this times magnesium, and so on and so forth. So each variable will have that, but the loading of these variables will be different. And I'll talk about the loadings as well.
Yes, sir. Done.
All right. Okay. So next, what we're gonna do is we'll just plot these what we are seeing over here, right? The one that we saw, that these are the loadings as we call it. So let's import some of these packages. Pandas profiling is not needed, but import everything else. NumPy, Panda, Matplotlib, PyPlot, SPLT, Seaborn, and %matplotlib. Pandas profiling is not needed. And then once you are done with this, go ahead and type the next line as well, and that will generate the plot for you, the heat map.
Done.
Okay, awesome. Okay, so once you're done, I'm assuming everybody's done, or you need more time? Aditya, good? Okay. So then
Yeah.
these are what we just spoke about in terms of your like loading, right? So for example, the stronger colors mean that these are more variable. I mean, loading of these variables are higher. Huh? Yeah. So for yeah, right. I mean, so the way you're gonna read it, let's say this is the last component. So this is 0.27 times alcohol, 0.05, 0.035 times malic acid, and so on and so forth. So you can see what is the biggest value in this component. What is the biggest value, either positive or negative? Who can tell me? Magnesium is the biggest value, right? 0.73. Correct. So that means this component is strongly indexed on magnesium variable, right? What is the second most important variable in this component? Second most important is what is you're saying ash? I think phenols might be the second one, right? Negative 0.5, or you have some different loadings. Huh? Which one, Sigal sir? Where is it? I don't see that. No, no, I'm still looking at this component only. Horizontally, you have to look at, right? So this component has highest value is 0.73. Horizontally, this is the loading for that component. What is the next highest value? Like in absolute numbers, right? Negative 0.5, right? So you can say the top two factors or the top two variables in this component are magnesium and non-flavonoids phenols. The top two variables which sort of like explain this component are these two, right? Now, who can tell me that what are the top two components in the next principal component? Again, look horizontally. Top two components in this, or top two features in this component, huh? So let's look at this is the highest value, I believe, in absolute number. Sorry, this is the highest value, 0.54. And This is the highest value, right? Second highest value, right? So 0.54 is malic acid and negative 0.43 is hue, right? So you can see these are the top two variables in that component. What are the top two variables in this component? In the component two?
Ash and is ash and
Yeah, so we have ash and alkalinity of ash. So you
alkalinity.
can see like each component has a slightly different flavor of the top variables which are coming in. And that's the crux of the principal component, right? That they are actually trying to capture one dimension of your data and they're over indexing on that, even though they have like, some flavor of all the other variables, but there are a couple of key features which are actually there in those components. And that's the main concept behind that, right? So that's the interpretation of the chart. Now we will come to doing the data transformations. Till now, what we've done is we've fitted the PCA, right? Remember in the like original approach that we follow, we do create the instant, fit the data and predict. But there's nothing to predict over here because it's an unsupervised learning. So when we don't do the predict, we do fit transform. We will convert our original data, fit transform. Instead of doing a prediction, because this is an unsupervised learning, we don't predict anything over here. We do the fit transform. So till now, what we have done is we know that our original data was 178 rows, 13 columns. I am now saying PCA that we have formed with 5 components. I want to transform my this data features. And after I do the transformation, I end up with 178.5. What does it mean? 178.5. Right. So till now, what you've done is I'll just take you over here, right? We decided what should be the right. We first of all, we fitted the data, right? Original. Then we decided 5 is the right number of component for me. Then we fitted one more time a PCA with the 5 component, and then we just explain what those components are and so on and so forth, right? You just fitted that, right? I mean, what should be right? Now, what you're doing is you will convert your original X data to the components now. Original, so I'll just draw it in Excel file for the benefit of others as well. What happened here? Yeah. So what is happening now is this, that your data was X1, X2, X3 till X13. You found out that 5 PCs are the right number of components. So now this is not going to be X1, it will be PC1, PC2, PC3, PC4, and PC5, right? So these, like, so for example, these columns have been reduced to the components now in a way that we have discussed earlier on. No, that's like, for example, this value, which is going to be P1 right here, will be again a linear combination of all these values for that particular observation. So the number of rows were 178, they are still 178. But this value, which was there in that, like, all these values were there. Let's say I'm just making up 1, 2, 3, 4, 13. These were the values I had originally. Now this is nothing but alpha 1, 1 plus alpha 2, 2 plus alpha 3, 3, like that. So they have been reduced from these original values to 5 components using that linear equation that we have spoken about earlier, right? So they are summarization of that. So now they're not the original values. So that's what basically this scaling will do. And when you come back and look at this, you can see that indeed my 13 features have now been reduced to 5 features, while the number of rows remain the same. Are we good, everyone?
Just a minute.
And then this is where we are creating our data frame. So we just did the transformation. I'm creating a data frame so that I have a column name as well. So P1, P2, P3, P4, P5, and we're just creating a data frame. So I'll wait for you to confirm that as well. And then we're doing the head and the shape. So if you remember, this value 3.31 is now a linear combination of your 13 values that we saw earlier on. P2 is a linear combination of those 13 values that we saw earlier, right? And not only that, what we're going to do while you're typing this, let me just do this very quickly. I will generate a heat map as well. Or is it already there? No, it's not there. So I'll wait for you to confirm first, then we'll talk about the heat map.
You're done.
Okay, in the class, everyone done?
Sir, 1 minute, sir, please.
Yeah. Take your time, no problem.
Yeah, done.
PC, no, unsupervised learning could be anything. I mean, so like all the methods that we're talking about today are unsupervised, whether it's a clustering, PCA, or market basket. But PCA is more for dimension reduction. Or like, some people use PCA for the image improvement as well, like different applications of that. But I'm just showing you in a tabular data, which is the X and Y columns, not any image data, because that's not in the scope. But you can use the PCA for image rectification as well. So for example, let's say you have a very old image. It has like faded out and all of that. People do the PCA to get the features and then stitch the features to recreate the images as well. Right? So all of those are PCA application, but we are looking at the tabular data, which is X and Y, not the images. Okay, so then we are doing the correlation. Can anyone tell me how can I generate the heat map from this? Do you remember? SNS dot heat map. And then let's see if I type it correctly. X scaled dot this, and then just like what we've done over here, right? So heat map, you have to pass on this array and annotation true, right? So what we're gonna do is we'll follow this exactly the same thing. And the reason I'm showing you is that you can see what is the benefit in having this. So this is our array. Annotation is true. And let's run it. If it is correct, then you will get, okay, so let me just do one more thing, sorry. np.round two decimal places. There you go. What does it really mean? What is the significance of this? And first of all, what have we done? So the transformed data, which is this is our transform data. We have done the PC on it. We have done the transformation, which is a fit transform. Now we are doing a correlation on this, linear correlation. We are rounding it off to two decimal places, and then we are doing the heat map. Huh?
No correlation between the components.
Correct. Yeah. Correct. That's correct. Yeah, Nidhi, go ahead. Sorry. You're saying something?
So heatmap now says that there is no correlation between the components.
Exactly right. Right. So you can see that
Now we
the
can't
dimension
further
reduction,
reduce.
Exactly right. Yeah. So the dimensions, the components are not only capturing the 80% of the original data's value, but they are all orthogonal. Component one has nothing to do with the component two. Component two has nothing to do with the component three and one, and like all the combinations that you're looking at. So we fixed the multicollinearity as well that we were talking about in the very first lecture. That you should not be having variables which are correlated to each other, and that itself has a big boost in the model's performance because the coefficients are not confused anymore. Now, if you do the same picture for your original data, let's do that very quickly as well. Where was it? Yeah. So let's say, yeah. So let's just do for the wine, the original wine data, right? So what do we do? SNS dot heat map. We will pass on wine anot is equal to true. Anot is nothing but the annotation, right? So this is what my wine data was originally, and just doing a heat map in that. And I'm saying, can you show me the original data's correlation? Uh-oh. So this looks really bad because it's okay. Let me remove the annotation because it's just too much to handle. Okay, hold on. Sorry, my bad, my bad. I'm not doing the core actually. That is missing. Now I can have the anot as well. That's why I was wondering what is it that I'm looking at. So you can see there's a lot of correlation, right? So for example, negative 0.7, negative 0.8, or I mean 0.8, whatever. I think yeah, it's negative because the dark is that, right? And all of that. In fact, if this becomes confusing for you, let's do the CMAP. CMAP is blue, or is it blues? Let's see. Huh? Yeah, we can try different things. Blues. Right. So now you can see, I mean, like higher the color, more the correlation, right? So you can see there are a lot of variables which are actually very significantly correlated. So there's tons of correlation that we're looking at, right? So that's what we have fixed when we did this dimensional reduction, that there's no correlation at all. So I will give you the assignment to do the same exercise on Boston and then see what really comes out from there, right? But I'm not going to do that because I have two more topics to cover. So I hope this makes sense what the PCA has done and so on and so forth. Now, what we'll be doing is it may or may not necessarily show you the benefits, so don't be worried about that. So one data, like the original data that we had, we will go and fit this model, right? So go back to your original data, not the PCA. I'm going to show you what we're doing just as a concept. So what we will do is we will go to our original data and we will fit, what are we fitting here? We will fit a random forest classifier on the original data, on this data. And we will see how much time it took us to fit on this data and what were the accuracy numbers and so on and so forth on the original data. And then we will fit one more random forest classifier, which will be on the principal components. And we'll see whether we can reduce the time that it took us to fit the data and how's the model performance, right? Because that's the end-to-end flow. We'll do exactly the same thing, but now this time on the components data, not that. And then we'll see whether we get a better performance, right? So in this case, I think 1.8, 1.8, or maybe just let's look at the weighted average, 0.91, 0.89, 0.89. Let's see how it looked vis-a-vis the original data. Point 0.97, 0.97, 0.97. So in this case, actually, the original data's performance is better than the PCA. So that's what I'm saying. It may or may not necessarily work out for you. But let's go ahead and give it a try. Let's see what comes out over here, right? So what we will be doing is we'll fit one random, or I can give you this as a homework. You can try it at home also. I'm okay with that. So Boston data, yeah, you can try it out, right? Correct, correct. So what basically we are doing is we are fitting a random forest over here. And once we fit it on the original data, which is the X scaled, which is 13 columns. Then we will do exactly the same thing, but we will do on the scaled, which is 5 columns. So I'm just going to run it on my side just to see what really comes out from over here. So allow me a moment. You don't have to necessarily follow me. It should not take very long time also to fit. This is the wine data only. On the wine data only, I'm fitting that model. I'm going to time it as well. So I'll just explain you what the time thing over here does that to see how much time it took me to fit that, right? So what we're doing over here is we are starting the time over here. So import the package called time.time will be the start. So it will basically look at the system time, what time you started this processing. It has noted down. Then I'm fitting all of this, which is the grid search on the random forest and all of that. And then once it has fitted the data, I'm saying time.time, which is the end time. And the end time minus the start time is going to be total training time, which it took me for this model. So that's what is going to come out over here. So I'll wait for it to spit out some output and then I'll move on. At least time wise, hopefully you'll see the difference that, I mean, if I'm fitting on the principal component, it takes less time for us to generate the model. Correct. That's correct. That's correct. You don't have to follow. I mean, Pranesh, you don't have to follow. You just like something that you'll do later on. But I want to generate this output and then we can take a break and then come back and begin with the clustering. While it is doing this, let me just give you, I think, Amarnath, you brought up the algorithm called as KNN. Does anyone know what is KNN? What does it really mean? It's very, very easy to fit and very lazy algorithm, right? What does the KNN really mean? And I'll give you some like links that you can try out later on, but I'll just explain you the main concept. No, yeah, it's called the K nearest neighbor, right? I will not necessarily fit a model end to end, but I'll just give you some links, which is very, very easy. I'll just talk about the concept K nearest neighbors, right? And the algorithm is really lazy in a sense that let's say I have so let's say I want to figure out whether the cross mark is a zero or the question mark is a zero or a cross, right? So it will say, I'm going to look at, so if you say, go ahead and look at 5 nearest neighbor. So it will say, okay, let me figure out who are my 5 nearest neighbors in terms of the distance. So it'll say 1, 2, 3, 4, 5. So it's okay. You asked me to figure out what am I, whether I'm a zero or a cross. And you told me to look at your 5 nearest neighbors. So I'm just going to look at the distance and say, who are my 5 nearest neighbors? 1, 2, 3, 4, 5. and so, okay, let me just do this. In my 5 nearest neighbors, I have 3 x's and 2 zeros, right? So I am a x. That's the logic of a k nearest neighbor. It's as simple as that, right? So this is not really any other things. The only thing that you have to watch for over here is that you do the distance, because it's going to compute the distances. So it's important that you do the scaling of the variable. Otherwise, the distances will be messed up. So that's important, right? If let's say what will happen, what will be the class of this if I say look at the 9 nearest neighbor? What do you think with the question mark will be now? 9 nearest neighbor. Hmm? Right. So 5 are already accounted for. Let's say this is the 6th, 7th, 8th, and 9th, right? So now you can see if I'm looking at this subset of the data, it's more zeros. So now the class will be 0. That's the logic, right? And the implementation is really simple actually in the k nearest neighbor, but it's a very, very simplistic model. It's not going to work for anything complex, right? But it's a great thing for you to be doing on a simpler data. So sklearn, knn. Right. So you can say, just like what we've done, by default, it will choose 5, but you can try different settings, like we have done the grid search, and then see what really works out better for you. K nearest neighbor 5, and then certain algorithms, certain metrics. We'll talk about these metrics in our clustering. So right now, by default, it uses the Minkowski distance, but you can change it to Euclidean and other distances. I mean, I think it will be here somewhere. Right, so you can change it to the Euclidean distance, Manhattan distances, and so on and so forth. All those can be done, but that's what the logic is. And I think they might have an example as well. Right, so for example, X is this, Y is this. I'm going to fit the K nearest neighbor, this. You can do the fit, and then you can do the predict on the new data, just like any other algorithm. So it's quite simple to implement, but very, very simplistic in the approach. So that's why it's not really very, very popular with more complex models that we're looking at, right? So that's the K nearest neighbor. And while it is running the code, let's and regression and regression. What will happen in the regression? So let's say same example. Basically, the concept it uses is this birds of same feather. If I am saying that correctly, flock together, right? So if you know who are your neighbors, I can tell you pretty much about yourself, right? So for example, you'll not say a billionaire living in slum area like Dharavi. I mean, there might be some billionaires living there, but I mean, that's abnormal thing, right? So if you want to see where are the billionaires living, you look at their neighborhood, right? So that's the same thing. So let's say same thing in a regression problem. I want to estimate what is the salary this person is earning, right? So I'm just going to make up certain data. So let's say I don't know the salary of this person. So I'll say, what is the salary of this person? So I'm going to say, look at the 5 nearest neighbor, 1, 2, 3, 4, 5. What will be the salary of this person? 10, 11, 12, 13, 15 divided by 5. That's the logic. It's very, very simplistic model. That's why it's called a lazy learner. It doesn't do any fitting, anything at all. Once you ask it to do, then it's okay. Let me go and look at your neighbor. It's a lazy learner, right? Versus the more greedy learner like a decision tree. It will try to classify everything, create the branches everywhere, right? And it's computationally less intensive as well because it doesn't do the classification until it get to that stage. Okay, so my output has come over here, people. It took me 479 seconds to run it, right? The decision tree on this. And if I go and look at the parameters, I'm just going to generate that. You don't have to work with me, but I'm just going to show you the benefit in doing that, right? And the features and everything as we typically do. But I'm more interested in the accuracy performance or this one. So it came out as this 0.97, 0.97, 0.97, which is pretty good actually. And then what we're going to do is exactly the same thing, but you'll see that it's going to take less time now to fit the model, at least at a bare minimum. So what we're doing is exactly the same thing, but instead of fitting on the data which was 13 rows, I'm fitting on this transform data, the PCA data. exactly the same parameter setting if I haven't messed up anything. Should be the same. And then I'm clocking that time again. So that's what it's gonna come back and tell me. And once you're back from the break, then we'll take a look. So this is 12:10. So shall we take a 10 or 15 minutes? Or no break? Take a break? 10 minutes or 15 minutes? 10 minutes. So let's be back by 12:20, folks, and then we will talk about the clustering. Yeah. Let's take a quick 10-minute break. By the time the output will be there, and then we can quickly take a look and then move on to the clustering. Thank you.
Not touching. I'm touching. This code, this code now after all, if I have it, you can actually. Up, up. So if you're afterwards, if you see the video, that'll be easy. You can easily reproduce. ठीक है.
So you're getting the error in the map. You should be running on the data frame. So can you just check the type is data frame, or you have the array? No, we converted that into a data frame over here. I think this might be a step that you would not have done. Uh-huh. You are getting this output. Okay, why don't you share your screen? You're there on the bridge so that others can also see. Hmm? Yeah, separate the noise from the signal.
Sir, I am getting a perfect classification.
Perfect classification with the PCA.
Yes.
Okay. We'll take a look. Somebody's unmuted. Can you just mute yourself in the class? So I think my output has also come in. Let's see the moment of truth over here.
I have not used grid search, a simple vanilla random forest.
Okay, got it. No problem. So let me just take a look at this one first, and then you can share your screen as well.
Yeah.
This one is fitting on the transform. So it took us 448, and of course, as a function of your system, whether it's slowed down by other activities. So 448 for the PCA one, and 479 for the normal one. So slight reduction in the fitting time, but because the data itself is quite small, that may not necessarily be significant, but you'll see that this will turn out to be important in certain cases, right? 479 to 448. I'm using random forest. Same parameters, everything. So you can see some reduction in the fitting time. And then the model evaluation also we'll take a look at. Model evaluation is identical actually. So you can see that we haven't lost. No, hold on. So I think I'm looking at the previous one. Yeah, in this case, the model performance has gone down, but by not that much, right? So 0.91, 0.89, 0.89 with significantly less number of features that we're looking at. So definitely, good jump in terms of the production and number of variables without losing too much signal and some gain in the fitting time as well. Yeah, yeah. That's correct. Amit, how about you? Is it working for you? So let's go to Amit first, and then we'll come to you, Krishna.
Okay.
You can just share your screen and then mute yourself, and then we'll try to troubleshoot. Because others will also be interested, right? Control Shift E. Control Shift E. Y always remains Y. Yeah. Now you can go to your code. Go up, go up, go up. No, previous one. Yeah. Can you do the X scale transform dot head? The line over here. Just do the head. Yeah. Instead of displaying everything, just do a head just to confirm. No, in line number 37. After line number 37, just do X scaled underscore transform dot head. Because that's where you're creating the data frame. So you should be looking at after that. Correct. So that's why I'm saying that yours is not a data frame. That's why actually having the error, right? So it is not able to. So just to rerun the code somewhere, yeah. So now it'll be there. Yeah. Okay. Fine. Great. Now, Krishna Kumar, you can share your screen.
Yeah. Sir, I'm sharing my screen. Let me know once you see that.
Yeah, you can see it.
Okay, so I have two questions. First of all, okay, so here I try to do a head of it of the X data and the Y. So this was my X as a head, 5 records, and this was a complete Y. So that's how. Then I try to do a shape of it for the X and Y. So they do match, right? And then I did a test train split on the this one, this X scale transformation. Y is this one, Y is Y with a 20% split. Then all this is some imports, creating a class of that model, doing a fit on this, the data, because this is a X train, X test, Y train, Y test out of this transform data. So if you see that the score of the model is 1, error is 0, error is 0, and then perfect 1, 1, 1, 1.
Yeah. So one of the reasons could be because you haven't done the grid search, right? So it might be overfitting on your train and test data in this case. So when you do the grid search, you'll get a more balanced analysis.
Sir, I have to ask one more thing. I'm getting a lot of noise.
I think somebody is unmuted. Can you mute, please?
Guys, can you mute yourself, please?
There you go. Okay, yeah. Now we
Okay.
can hear you.
Yes. So now it's fine for me also, sir. Sir, so last time when you gave us an assignment to do that, when doing a grid search, so what was happening is when I was trying to run this 2-3 times. So suppose if I run it one more time, this time I will get 97, 97, 97. I will show you right now. So here, shift enter. You see, okay, 95, 95, 94. If I do it again, this changes to 1.
Yeah.
So,
right. So that's
I don't
basically
know
a
why.
typical. Yeah, it's a typical symptom of overfitting. When you are like doing it again and again, you're getting different results because there's some amount of uncertainty or some amount of overfitting in your data. But the grid search will not vary that much because you're doing a much more robust approach there.
So for grid search also, it was varying, and then the maximum I could attend from grid search was 97.
That's correct.
And the minimum that I could reach was 94 point something.
That's correct.
But I was not able to bring it up. I mean, more higher than 97.
Yeah. No, when you actually compete for any Kaggle competition or anything of that nature, or even when you're thinking about the practical application of your model, your accuracy on this data does not matter so much. What matters is the completely you have given, like, you have fitted a model, then they will ask you to score another data set that you haven't done the train and test on. And that is what matters. So you'll see there are a lot of people who will get a fantastic result like you are getting, in this case, 111, right? But
Yeah.
when I throw in that brand new data, your model will rank lower than somebody who has done the grid search, right? Because the grid search is generalizing well. It's looking at, building a more robust model. So when you get 111, you definitely are looking at the overfitted model. So it may look very good, fantastic on your this data, but the moment I give you a brand new data, and let's say I've done with the grid search, which is 0.97, 0.98, my model will most likely rank higher than your model, right? On that unseen data that we both are given. So that's the concept of the grid search, or doing, more cross validation and stuff like that, because it's a much more generalizable model. So not just grid search, but I'm saying grid search along with the cross validation. That
Yeah.
is a more robust approach, not
Uh,
necessarily this classical approach.
One more thing. So while doing a feature space exploration, I mean the parameter space that I was putting, I tried to run some 5, 6 different times, and then every time I was moving towards those numbers which were giving me a better test result.
Yeah.
But it took something like 6 or 7 iterations, if I remember. I mean, like I started with like 10, 100, 200, 1000. Then I moved back towards okay between 100 and 150. So like that. So I mean, I started with some bigger numbers from minimum to maximum. Then I started, going towards down towards the a much smaller feature space for those parameters. Um, I mean, it took a lot of time for it. I mean, the training time itself, the first time it was something like for 1000 trees, it was like some 17 or 18 minutes. But
Yeah.
how do I do
Yeah.
in exam?
Right. No, I mean, I think the typical approach that you should follow is, don't use the train and test approach. Use the cross validation and grid search approach, right? And within that, if you run your model multiple times, you may get slightly different results. That's where your, the seed, random seed will be important. If you generate the same seed and use the same seed, then it will be much more robust.
Um, okay, so let me show you.
Sure.
Yeah. So, okay, so one was this and one was this, right? So these two. So when I started doing this, I mean, I named this file as 94 IBNY. Um, yeah. So initially, I mean, this was like initially when I started, it was like 10, 100 and 1000, right? So I was talking about this one. And then I had uh, some more values than I restricted here. And then I mean, it took a lot of time for me to reach out to these specific numbers. I mean, to come down towards only these ones. And then when I trained again with some, I mean, when I ran the same code again without any change, uh, this one is with 97% accuracy. So I do not know what was happening, but then, I mean, if I run this one, instead of giving me 94, this can give me 97 also. So I was not sure what was happening.
Yeah.
I will,
No, I think,
yeah,
I
so
mean,
you see this?
right. Yeah. Right. So the number of estimators that you're trying, in my view, are slightly limited actually. So you should go ahead and give it a more
Uh,
try. Right.
Sir,
Just a second.
actually, yeah.
Hello. अच्छा अच्छा मैं करता भी आपको 1 मिनट कॉल. हाँ. Sorry. Go ahead.
So, sir, when I started, it was like 1, 2, 3, 5, 7, 50. I mean, I took all the prime numbers. I had a
Mhm.
bigger sample space here, bigger sample space here, bigger sample space here. And with the time and on, I started decreasing one because whatever the value I got for the first one, I started giving it somewhat lesser than that, somewhat more than that. and then later on I thought, I mean, I came to know that these are the numbers that's going to give me the best ones. But then
Right.
these are very consistent. I mean, when I run one time, it will give me 97, another time it will give me 94%. But only these were the two fluctuations with this set of data.
Got it. Got it. Yeah.
So
So
for example, even if you see the class weight,
yeah.
so I try to do everything. Even I do the square root. I do some other things also. Sometimes bootstrap, sometimes without that. So I mean, I try to, but
No,
then
I
why this
understand.
was unstable?
I mean, that level of instability will be there, so that is not necessarily that big a deal, right? So as long as you're getting the values which are within plus minus 10%, that is understood, right? Because it just depends on your randomization. So one thing that I can see is that you don't have a random seed in your model, in your instance. So if you say random seed is 999, it will recreate the same output.
Okay, so next time onwards, I will try to adding random seed as
Yeah,
well.
yeah.
Yeah.
Otherwise,
Then
it just depends
yeah.
on how the model has optimized. So you will see certain amount of uncertainty coming in. I'm not surprised, but it shouldn't be like day and night different, right? It should be like roundabout in the same way.
So these many hyperparameters I have explored. I mean, it took lot and lot of time. I think
Ah,
around 1.5 hours to two to come to these values.
got it, got it.
Yeah. So that's it, sir. I mean, and again, while doing in the class right now, I mean, when I was doing it, sometimes I was getting perfect one, other times 94, other times 97. So thought of asking you that why I'm getting this.
Uh-huh. No, yeah, I think one thing is definitely random seed. Try it out, and
Okay.
then see how much variation you are getting from there.
Okay. Okay, I will do that. Thank you, sir.
Sure. Hmm? Okay. That's okay. I think some amount of those values will be there. Whichever is the score that you've used is basically that is being shown, right? So I think last time we were using the scorer. I think it's over here, right? So somewhere we are defining the scorer as well. Let me see where exactly we're defining. Right. So scorer is basically the recall. So when it says the best score, that means you're looking at the best recall value, and that too the weighted average recall value for the multi-class classification, not just for one class, but for the weighted average. Weighted meaning in terms of number of observations that you have. So it's when you say best score, that basically what it means is that you're optimizing for the recall. Now you can do precision, you can do ROC, you can do accuracy. It just depends on what your ultimate metrics are. Yeah. Awesome. So folks, in interest of time, shall we move on? So what I'm going to do is, I don't know how many of you have done the reading. Oops, sorry, not this one. Very quickly take maybe 10-15 minutes to go through these couple of articles on the clustering, 32 and 33. So this is 12:40. By 12:50, we will kick off with some of the conceptual discussions, right? And then maybe once we are back from the lunch, then I will begin with the actual coding. But go ahead and take a look at the article number 32 and 33. And we will talk about how it works and all of that. What is a k-means? What is a hierarchical clustering? All of that. And then we'll begin with some hands-on exercise. And then we will jump to the other one. And then I'll give you the homework or the classwork combo that you can work on together. But article number 32 and 33, 32 is particularly more important because it has a link. So if you go to the 32, it says as highlighted in this article, clustering and segmentation. So if you click on that article, it will take you to Quora page that I've written. And then there is a SaaS article over here. There is a some business article. So if we can just take it those two first, and then we will come back and discuss that, right?
Excuse me,
That's
sir.
the plan for the next 10 minutes.
Excuse me, sir. Excuse me, sir.
Chirag, this is the same link which you have shared in the group, right? Which is said to read.
Which link?
The link which you have shared, that one only we have to read, right? In the
Yeah.
group.
1 second. Article 32 and 33 is also there. I'll just confirm once.
Yeah. Can you please share the links? It will be good.
Yeah, sure.
Thank you.
Yeah, give 2 more minutes.
Excuse me, sir.
Hmm?
Sir, 1 o'clock we are having meeting like for the regarding placement. So all the participants must join that meeting.
1 o'clock, you have a meeting on placement. Acha, okay, got it. Yeah. Till
Yes.
what time?
1 to 1:30.
1 to 1:30. That's okay. So we can just talk some of the conceptual things and then we can break at 1 o'clock.
Okay, sir.
Where is this meeting, Chirag?
I have shared the link in the group, sir.
Okay, okay. Got it. Anyone who would like to share what you have understood about the segmentation, where exactly it is used, what is the utility? Aditya, you feeling cold? Anyone? What is the use of segmentation or clustering? Or if you're still going through, you can. Not a problem.
So segmentation or clustering is like based on the same features, group things together.
Yeah, correct, Nidhi. Can you give some examples?
Uh, like fruits, vegetables. I mean, in the fruits, if we have like a 3, 4 types of fruit, and then in the vegetables, if we have different vegetables, then we can group it
No,
like okay,
so no, build more. What 3, 4 types of fruits you are saying? Like, I mean, how
apple,
would you
banana,
segment?
mango.
But they are
How?
not segment actually.
Yeah, it will not be a good example. Let me think.
Yeah, they are not segments though. I mean, they are different types. What do you mean by the segments? Like, I mean, group. A group which are like, I mean, all the people or all the members in that group are similar.
Male,
So,
female group.
right. Right. So yeah, male, female, like for example, that's a very simple segmentation. Males on this side, females on this side, right? You talking about the age, right? So people less than 30. Iris data set, yeah. Yeah, correct. Yeah. We will form the groups there actually. If you want to do it, I mean, we can form the groups there and see how many natural flowers come out, right? But the segmentation is pretty much everywhere, right? So you will see prime, non-prime customer, right? You will see based on demographics, higher income, middle income, lower income. I mean, government used to have the houses, they still do LIG, MIG, HIG, right? So all of those things. I mean, those are nothing but the segmentations, right? Why is it important? I mean, I'm not going to go through a lot of details because we are rushing against the clock over here. But segmentation forms a very, very important. And when we do the MBA related discussion, you'll see that it forms a very, very vital strategy in business for STP. S stands for segmentation. T stands for targeting or target. And P stands for positioning, right? So for example, let's say if I'm an auto car maker, right? Let's say if I'm BMW or Mercedes, right? So BMW and Mercedes must understand what are the different segments of car buyers in India.
Excuse me, sir.
Yeah.
Are you sharing screen?
Oh, okay, my bad. Thanks for reminding. Right. So segmentation, targeting, and positioning. So for example, if I'm a BMW or Merc, right? I mean, I would like to understand what are the different segments of car buyers that we have. Then they will say, I want to target this segment only. For example, you can say that if I'm a Mercedes or a BMW, I'm not targeting a mass market, right? I'm not targeting people who are lower middle income. I'm talking about more affluent class, right? People who may own business, executives in the multinational companies, people having a certain income and higher and all of that. So that's what we call as a targeting, that you're not running blindly after everyone. You cannot be everything to everyone. If you try to be everything to everyone, you are nowhere. So that's where you have to be really focused on what you want to target, right? And then the last one is positioning. Positioning is then your entire product strategy, your entire marketing, right? All of the things that we do in a typical, like, selling of the product should position accordingly, right? So then if you're a BMW or Mercedes car maker, you're not going to advertise your cars in, let's say, um, like, flea market, right? I mean, because your clientele is not going to be there. You're going to advertise more in golf courses. You're going to advertise in more those magazines, right, or publications where you see that your clientele is there. That's about the positioning, right? And how do you actually? They will not say 10% off on this, right? They will actually sell the features that, I mean, this car has the coolest features, right? Things of that nature. That's what basically the positioning really boils down to. That you have segmentation, target, and then positioning, right? So that's the broader business use. In terms of the analytics, this segmentation is nothing but what we call as a clustering, right? And clustering is nothing but grouping. So you can say group one, group two, group three. And this group, basically what it means is that the people who belong or the objects who belong to group one, they should be similar to each other. And we'll define those similarity metrics and all of that. People who are in this group two, they should be similar to each other. And people who are in group three, they should be similar to each other. And they should be different from each other. If they're all similar, but they're all similar to each other also, then those clusters are not necessarily valid clusters. So they should be different from each other, but similar to within the cluster, right? There are some metrics that we'll be talking about in terms of defining that cluster, right? And because we are doing more like a grouping, there is no dependent variable over here or label. Will this be a supervised or unsupervised learning? This will be unsupervised learning, right? So you're not necessarily targeting any particular variable and all of that. This is an unsupervised learning where you're just trying to group the objects, right? And how do we group them? Let's say we have x1, x2, x3, x4 till xn, right? And then you have rows n1, n2, n3 till nn. What you're doing is basically you're saying that I will figure out based on these features which variables or I mean which rows are common. So you can say n1, n3, and n11, and so on and so forth have similar x1, x2, x3, xn. So they should belong to one cluster, right? Similarly, some other rows will belong to another cluster. That's what basically the whole clustering algorithm is, right? Hmm? Right. So these observations will be grouped together based on these features. So they will define which features are similar. When I say similar, I'm just going to make up certain small example, very, very small baby example. Let's say income and sorry, let's say age and income, right? I'm just going to make some data over here. Right? So basically, it will be like, age for this cluster, let's say cluster one, cluster two, and there will be always something which is looking more like, unstable sort of thing, cluster three. So cluster one, for example, how would you define that cluster? Huh? Cluster one is people who are, let's say, low on age and low on income, right? So these were the two variables that I'm using to define the clusters. So people who are low on age and low on income. That's what my cluster one is. I'm defining based on, let's say, these variables, right? Cluster two is people who are, yeah, so high income people, middle age and all of that, right? And then cluster three is that, you are high on age and low income, right? So basically typical life cycle like that you all go through, right? I mean, that you are, when you're young, your salary is low. When you're in the middle of your age, your salary peaks. And then again, when you sort of like, go to the retirement age, then your salary drops again, right? So that's basically the concept, right? So you can see three clusters have been formed on the two dimensions, age and income. And that is what the algorithm does to find the people who should belong to this cluster or should belong to some other cluster. That's the main purpose. That's the concept of the clustering. I will take a break over here. I think, in fact, what we can do is you have till 1:30 that meeting, and then you can go for lunch. And by what time, Chirag, we can be back? I mean, 1:30 will be sharp ending at 1:30, or that will be extended? What is your
RP, we are in this session. I will not take more than 15 minutes. Right?
Okay.
So by maximum by 2:15, we must be back. Yeah.
Okay. So then
Yeah.
let's do this. Thank you,
Yeah.
Shinu. So
Yeah.
let's do this then, folks. Take a break now. Go attend the session because the session is live. Combine that with your lunch break and be back by latest 2:15 because we got clustering and then we got one more topic to cover today, right? Sounds good?
Okay.
Thank you.
Thank you.
So please join the other session. No? Thank you.
Yeah. Can you send me the link? Send me the
Yes,
link,
sir.
please.
Yes, sir.
Yeah. So I'll go out from this and then join that session. Okay. This is the one, right? Chirag has sent also.
Yes, sir.